Hello, my name is Evan Chan, and this is my Physics 2212 Lab 3 lab report. For my introduction, the purpose of this lab was to observe magnetic fields through an experiment involving a bar magnet and a cell phone app. Using these tools, we wanted to see the relationship between magnetic fields and distance, and to also use these distance-dependent magnetic fields and the Biot-Savart law to find the magnetic component of the bar magnet. The physics principles I used during these labs were the Biot-Savart law, distance dependence formula, linearization formula, as you can see down here. The main results of the lab were that I got mu to be equal to 2.28 amp raised meters squared, and n to be negative 3.07, k to be 4.568 times 10 to the negative 7th power. And the assumptions that were made during this lab were that the magnet was treated as a magnetic dipole, and the Earth's magnetic pole is negligible. The initial conditions was that the x value of the magnetic field was as close to zero as possible. The system was the bar magnet, and the surroundings was everything else. For the experiment, first the phone had to be rotated so that the magnetic field in the x direction was as close to zero as possible. Then the phone was to be slid on a ruler perpendicularly, both vertically and horizontally, with the bar magnet on one end of the ruler. This allowed us to determine the position at which the magnet had the strongest magnetic field reading. And for the main experiment, we found the on-axis distance from the bar magnet to the magnetometer for values of 20, 70, 110, 170, and 220 microteslas by using a ruler and moving the magnetometer until these values were seen on the magnetometer. And these values were then linearized and graphed, as you can see here on the graph. For part 2 of the experiment, we found the off-axis magnetic field of the bar by using the same setup for the on-axis field. We first found a distance for which the magnetic field had a magnitude of 100 microteslas and recorded it along with the y component of the Earth's magnetic field at the same location. Then we added a second ruler to the first one and aligned the location of the sensor on our phone and moved the phone the same distance for the y component of the Earth's magnetic field. Finally, we found the correct y component for the net magnetic field to account for the Earth's magnetic field by either subtracting or adding by to/from bx. For my observations, I found that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And for my second one, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. For my calculations for the mu value, I used these three equations, the Biot-Savart law, distance dependence, linearization. For the distance dependence equation, I got this from the graph that you saw earlier, and for my n value, it was just the slope of this equation right here, and then for the ln of k, it was the y-axis of this one. It was negative 14.599, and then you just take the e to the power of ln of k on both sides, and then that gave me a k value of 4.568 times 10 to the negative 7th, and then using Biot-Savart law and the distance dependence equation, I solved for mu as I set them equal to each other, and I got mu to be equal to 2.28. For my code, as you can see here, this just calculated the magnitude of r, and found the r hat value, and then this is just the Biot-Savart law in code. And then for this one, it was just finding four perpendicular to the axis and the observation locations. For this, it's drawing arrows. This one's also drawing arrows, but this is for perpendicular to the axis. And for this part, just setting the average dperp value from our experiment equal to the dperp variable. And for this one, this was calculated to be my observation location 45 degrees, and then this is just drawing the arrows. And this is what my code result looked like with my values all right here. For my discussion of similarities and differences, the theoretical off-axis field that I got was 2.7 times 10 to the negative 5th teslas. The experimental off-axis field was 6.37 11 times 10 to the negative 5 Teslas, so the percent difference was 80.92, and this is my B at 45 degrees at a distance D. For the what if, the results would have been skewed to some degree as the Earth's magnetic field would have changed the x value as the phone moved. And for the what if, the two magnets would have a larger dipole moment due to their added magnetic fields, and this would cause the value of n to be larger as well. This would also create larger charge changes the larger the distances are from the magnet.